So now that we're familiar with adsorption as a process of molecules attaching to a surface, let's see if we can make some progress by developing a model, a physical chemistry model, to understand adsorption more quantitatively. So this model is going to be called the Langmuir Adsorption model. So this model, of course, consists of some phase like a gas phase or perhaps a solution phase, where we have molecules up in this upper phase that then can desorb onto a surface and then attach to a surface. We can assume that the molecules in the gas phase are not interacting with each other. So when a molecule is in the gas phase, it has an energy of 0. When a molecule is attached to the surface, then it has an energy where it's interacting with the surface. So we say that energy when it's attached to a surface has some value epsilon. And we'd expect that in most cases that value of epsilon would be negative. The other thing we can assume about our surface is we can make this a lattice model, meaning we divide the surface up into a bunch of different individual sites, lattice sites, where the molecules can absorb. So we'll make those sites of a size that only one adsorbate molecule can fit into each one of these lattice sites on the surface. So for a given surface area, a given surface size, that we have some fixed number of adsorption sites. We'll use capital M for that number of adsorption sites. And as we said, there's only one molecule of the adsorbate that can attach to each one of the lattice sites. And we're also going to further assume that no molecules on the surface interact with each other, which means that even if some molecule adsorbs next to another molecule, it still has an energy of epsilon, even though it's next to another molecule. We don't allow it to interact with that molecule and have a different adsorption energy depending on whether it's next to another molecule or far away from other molecules. So that is our lattice model for adsorption. Again, that's called the Langmuir model. We can say, to begin to understand the physical chemistry of the system, we can say, let's suppose of those M sites, N of them are occupied. We have N molecules, capital N molecules adsorbed onto the surface. So there are M places to put those molecules, and I've got N of them occupied, so that there's a degeneracy. There's going to be M choose N, different number of arrangements of those N molecules on the M lattice sites. So that's this collection of factorials. And then if I have N molecules attached to the surface, each of which has an energy epsilon, the total amount of energy in the system is N times epsilon, remembering that the molecules in the gas phase have 0 energy. So what that means is I can write down a partition function. So the Boltzmann factor for the N molecules attached to the surface, they have a total energy, some energy E, so the Boltzmann factor looks like E to the minus energy over KT multiplied by the degeneracy. So we know the degeneracy and the energy, so we can write this as this binomial factor multiplied by E to the minus N epsilon divided by KT. So that partition function will allow us to understand exactly where the equilibrium lies between molecules in the gas phase and molecules on the surface. If we are at equilibrium, the equilibrium condition tells us that the chemical potential in the two phases are equal to each other. Chemical potential in the gas phase is equal to the chemical potential in the adsorbed phase. We know what the chemical potential of a gas is, at least if it's an ideal gas. It's the standard state chemical potential plus KT log of the pressure relative to that standard state potential. So in writing down the equation here, I've just made an assumption that let's assume our chemical potential in our standard state chemical potential of the gas is 0. So I'm just going to ignore this last term, the standard state chemical potential. So the chemical potential in the gas phase depends on the pressure in this way as KT log pressure divided by standard pressure. The adsorbed phase, we're going to have to do a little more work to figure out what the chemical potential is. The chemical potential in any phase is the partial molar energy of some sort, depending on whether we're constant temperature, constant volume. In this case, it's going to be easiest to consider the chemical potential as the partial molar Helmholtz free energy with respect to the number of molecules. Normally, we would say we would want to do this at constant T and constant V. dA, dN at constant T and V is a definition of the chemical potential. In this case, if I go back to the diagram that describes the Langmuir model, the volume, constant volume, is essentially the size of the system. And the size of the system we're talking about is the number of sites to which the molecule can absorb. When we're talking purely about the adsorbed species, if I were to double the size of this system, I don't have a volume that I'm talking about, but I would be talking about doubling the size of the surface to which molecules can absorb. So the extensive variable that's equivalent to volume in this case is the number of sites, or the value of m. So that's why I'm taking dA dN at constant t and constant m rather than constant t and constant v, because there is no volume in the system. The equivalent of the volume is the surface area m of the system. So if I want to know the chemical potential on the adsorbed phase, I want to take dA dN at constant t and m. The Helmholtz free energy, we know the thermodynamic connection formula for how to figure out a Helmholtz free energy from the partition function. And I don't see both of those on the same screen, so if I zoom out a little bit, this partition function, if I insert the partition function we wrote above into the expression for the Helmholtz free energy, I need to take negative kT log of that partition function. The partition function is this ratio of factorials times an exponential. So the log of it is log of the numerator, m factorial, minus log of the denominator, which has an n factorial and an m minus n quantity factorial. And then the log of that exponential is just the exponent, minus n epsilon over kT. So now we can think about what to do with this expression, and as usual, whenever we see log of something factorial, our first thought is Stirling approximation. So as long as m is large, as long as n is large, as long as there's a lot of molecules attached to a fairly large surface, we can write the log of m factorial as m log m minus m. And likewise for the log of n factorial and the log of m minus n quantity factorial. And then I don't do anything yet with this minus n epsilon over kT. So this is an expression for A, and I could, if I want to, simplify a little bit and cancel some of these things out, but I'll do the cancellation in just a minute. What I do with the Helmholtz free energy is I want to use that to determine the chemical potential. So dA dN, remembering to do that at constant t and constant m. So if I take the derivative of this expression, the Helmholtz energy, with respect to n, all the terms with purely m's in them disappear. Derivative of n log n with respect to n gives me a minus log n term. When I take the derivative of this n and it becomes 1, or using the product rule, if I take the derivative of log n and log n becomes 1 over n, then I've got minus n times 1 over n. Derivative of n is 1. Derivative of, I need to use the product rule again for this term. If I take the derivative of this n, I've got a negative, negative, n becomes a 1, and I'm just left with log m minus n. Or for the other half of the product rule, I've got a minus m minus n. Derivative of log is 1 over m minus n, and the negative sign in front of the n means I cancel this negative sign. This m goes away, the derivative of this n is negative 1, and the derivative of minus n epsilon over kT is, well, minus epsilon over kT. So those are all the terms in the derivative. Now I can do some cancellation. I have a minus n over n, which cancels a plus 1. I've got a m minus n over m minus n, which cancels a negative 1. So after those cancellations, I'm left with a log m minus n minus log n, which I can write as log m minus n over n. The difference between these two logs is the log of the quotient. And I still have this minus epsilon over kT term. I'm going to rearrange those a little bit, mainly because these m and n quantities, those are extensive. Again, if we were to double the size of the system, m would double and n would double. I'd much rather write this in terms of intensive variables. So thinking ahead about how to do that, if I take this fraction m minus n divided by n, if I divide on the top and the bottom by m, so m becomes 1, n becomes n over m. The n in the denominator also becomes n over m. Then I've turned those extensive quantities into intensive quantities. So I've got 1 minus n over m, and then in the denominator an n over m. That quantity n over m, think about what that means for a second. That's the number of sites occupied on the surface divided by the total number of sites on the surface. So that's the fraction of sites on the surface that are occupied. So I can give that quantity a new variable, let's call it theta, and that'll be our surface coverage. If theta is 0, that's because there's no sites occupied on the surface. The largest theta is going to be is 1, and that's when all of the sites on the surface are occupied. If all m of the sites are occupied, then m sites occupied over m sites available gives a ratio of 1. So this number theta is going to be somewhere between 0 and 1, or 0 and 100%. So with that definition, I can rewrite the n minus m, n over m as a theta, and what I've got is that the chemical potential of the adsorbed species is minus kT times this quantity log 1 minus theta over theta minus epsilon over kT. That's the cleanest I can make the expression for the chemical potential of the adsorbed species. So now it's time to go back to our equilibrium condition and say if the chemical potential of the gas is equal to the chemical potential of the adsorbed species. We've just calculated the chemical potential of the adsorbed species. If we set that equal to the chemical potential in the gas phase that we had written down earlier, both those terms have a kT in them, so let's just cancel the kTs. And I've got log of pressure on the left is equal to this expression involving surface coverages and the binding energy on the right. The negative log I can use to invert the ratio, so it's the log of theta over 1 minus theta. So I've turned the argument of the log upside down. So this gives me an expression for how the pressure of the gas relates to the amount of surface coverage and the temperature and the energy of the binding of the adsorbate to the surface. So I'm going to rearrange that, and mainly what I'm interested in doing is I'm solving for the value of theta. I want to know at a given pressure and temperature, perhaps, how much of the surface is going to be occupied by adsorbed molecules. So if I rearrange this a little bit to solve for theta, first we can undo the natural log. So P over P naught is equal to, getting rid of the ln here, I've got theta over 1 minus theta, and then undoing the log required exponentiating, so I get e to the plus epsilon over kt. And now I just have to do some algebra and solve for theta. If I bring the 1 minus theta and the exponential over to the left-hand side, I've got this collection of terms and nothing on the right except this theta. Now I've got thetas on the left and the right, so if I bring all of the thetas back over to the right-hand side, I've got minus P over P naught e to the minus epsilon over kt. When I bring that over to the other side, it turns into a plus P over P naught e to the minus epsilon over kt, in addition to the 1 theta that was already there. So now I just divide away this term in parentheses to isolate theta, and it turns out theta is equal to this collection of pressures and exponentials. So notice that is now a function that tells me the value of theta if I know the pressure, and if I know the temperature, and if I know how tightly molecules bind to the surface when they attach. We can define a constant, capital K, if I collect almost all those terms, all but the pressure, because mainly what I'm doing is interested in doing is understanding how theta depends on the pressure. So if I collect all the terms that don't involve the pressure into this constant K, define that to be our binding constant, capital K, then that collection of terms shows up once in the numerator, once in the denominator, and I can rewrite this expression as Kp divided by 1 plus Kp. So that's an expression for how the surface coverage, what fraction of the surface is occupied, depends on the pressure of the gas. If I think about what that function looks like, if I graph constant times P divided by 1 plus the same constant times P, we notice a couple of things. First of all, in the case when Kp is a small number, that can happen either when the pressure is very low, so at low pressures, Or it can also happen when K is very low, and K is going to be low whenever the temperature is very high. So when Kp is a small number, there's a Kp in the numerator. The Kp in the denominator is small compared to 1, so I can ignore the Kp in the denominator. So then Kp divided by 1 just means the surface coverage scales linearly with pressure. So the surface coverage is my constant times P. So in other words, when I'm at low pressure, this function is just linearly increasing. On the other hand, when the opposite is true, when that product K times P is greater than 1, that could happen either when the pressure is very large or when K is very large, which corresponds to low temperatures. If Kp is a large number compared to 1, then the opposite is true. I can't ignore the value of Kp, but if Kp is large, I can ignore the value of 1. So then I end up with just Kp over Kp, so that ratio is close to 1. So when the pressure becomes very large, the surface coverage is close to 1 or approaching 1. So that's what's happening at large pressures. The surface coverage is approaching 100%. And that makes sense, again, from a Le Chatelier's principle point of view. If I increase the amount of molecules in the gas phase, that'll shift the equilibrium more towards the opposite side of the reaction, so it'll push more molecules onto the surface. Likewise, at low pressure, if I remove molecules from the gas phase, the surface coverage is going to decrease as molecules leave the surface to enter the gas phase and attempt to increase the pressure. But mathematically, this function that I've just sketched here has this form, and that's called a Langmuir isotherm. It's called an isotherm because this is describing the surface coverage as a function of pressure, but it's done at a particular value of temperature. Remember, K, this constant that we've defined, has the value of temperature in it. So the value of K will depend on the temperature. At any given temperature, we'll have an isotherm that describes how the surface coverage depends on temperature. Depends on pressure. If I were to do the same calculation at a different value of the temperature, if I were to move to a lower temperature, then when this temperature decreases, if we pause for a minute and remember that the epsilon is a negative number, so this exponent is positive because epsilon is a negative number. The binding energy to the surface is favorable. When the temperature decreases, this exponent gets larger because temperature is in the denominator, so K gets larger. And when K gets larger, this curve is going to look more, it's going to still be linear at low pressures and approach 1 at high temperatures, but it's going to do that more quickly with a higher temperature. So the graph is going to look more like this. So this would be for a temperature that's fairly large, a temperature that's hotter than the initial temperature. On the other hand, if the temperature is a large, that's wrong. So we did that in the case where T was a small number, so the exponent was large. So this would be what would happen for a cold temperature. The opposite is going to happen when T is large. When T is a large value, the positive exponent is going to become smaller, and K is going to become a smaller number. And what happens then is this function increases more slowly. It'll still increase linearly at first. It'll asymptotically approach 1 at high pressures, but it's biased towards lower amounts of molecules adsorbed to the surface at the high temperatures because entropy is dominating. So we have a number of these different curves at any given temperature. We have a particular curve. Colder temperatures have different shapes of these curves, similar shape, but a different speed with which the curve rises. So at cold temperatures or hot temperatures, we have different Langmuir isotherms. Notice that all these, the equation we've developed, this equation for the Langmuir isotherm, has relied on several different assumptions. So I'll just recap what those assumptions have been. We assumed, number one, that the system was in equilibrium. We assumed that the chemical potential of the gas phase and adsorb phase were equal. That was our equilibrium condition. So we're definitely assuming an equilibrium is going on. Some real-world adsorption problems are not in equilibrium. For example, chemisorption problems. Chemisorption processes, if a molecule dissociates when it attaches to a surface, if it changes its chemical binding, then that desorption process is not necessarily reversible, and those reactions won't necessarily be in equilibrium. We've also assumed that the molecules adsorb to the surface in only a single monolayer, only a single layer on the surface. And where we made that assumption was by saying that only one molecule can attach to the surface in each one of these binding sites. If the surface can be coated by more than one layer of molecule, then we could stack up molecules on top of each other, and there could be more than one molecule per binding site. So if this system undergoes multi-layer adsorption, if, let's say, water molecules don't just bind to the surface itself, but if the water molecules can then adsorb onto the water layer that's already present, that would be an example of multi-layer adsorption, and the Langmuir model wouldn't be expected to work very well. The third assumption that we've made is that each of these adsorption events is independent. We said that the binding energy epsilon is the same number regardless of whether neighboring lattice sites are occupied or not. In the real world, very often binding is cooperative, meaning if one molecule is attached to a surface, the binding energy to bind right next door is either larger or smaller, larger in the case of cooperative adsorption or smaller in the case of an anti-cooperative adsorption. And lastly, we assume that the large n, the value of n and m are both large in order to use the Stirling's approximation. And normally that's the case. Certainly most surfaces are large enough to contain many, many molecules, large enough that Stirling's approximation is a good approximation. But in the case where the surfaces that we're binding to are very, very small, a very small number of binding sites, then the Stirling's approximation portion of this derivation would fall apart. So we've made these assumptions, and there are certainly some adsorption processes for which these assumptions hold, but there's other cases in the real world where the assumptions don't hold. So this is what lets us know whether we're able to use Langmuir's approximation successfully or not in cases where those four approximations do hold.